Hello, my name is Andrew, and this is my Oscillations Lab for Physics 2211. For this lab, an object was attached to a spring and was pulled down, and its motion was recorded. I used tracker software to determine its position. Then I used a computational model to test the same experiment. The purpose was to analyze the motion of an object attached to an oscillating spring while swinging in an arc. It's also to compare a computational model to actual observed motion. The main result is that the model tracks the y position well but the x position poorly. The energies oscillate with the object and sum to zero, maintaining the energy principle. The position update formula and velocity update formula were used in the computational model and are both derived from Newton's second law. The spring force is equal to negative times the spring constant times S times L hat, where S is the change in length of the spring from its relaxed length. The gravitational potential energy is equal to mgh when the object is near Earth. The kinetic energy is equal to 1/2 times mass times velocity squared. The spring energy is equal to 1/2 times the spring constant times S squared. The energy principle is that the change in energy is equal to the sum of the change of all the other forms of energy in a system. The spring constant is equal to 4 times mass times pi squared all over the period of one oscillation squared. The relaxed length is equal to the magnitude of the length minus mg over the spring constant. The initial conditions of this lab is that the magnitude of the length is 0.7 meters. The mass of the object is 0.02 kilograms. The initial position of the object is 0.001 in the x and negative 0.841 in the y. It should be noted that the x value is much smaller than the y value. The object starts at rest, so its initial velocity is 0. The system is the object, and the surroundings are the earth, air, hand, and spring. On the right, there is a free body diagram of the moment when the ball is released. The gravitational force acts directly downwards, while the spring force acts up and slightly to the right. The spring force acts in the exact opposite direction as a vector to its initial position, relative to the origin. Running this experiment, I found that the period for oscillation is 1.52 seconds. Using this value, I found that the spring constant is 6.869 Newton meters, and the relaxed length is 0.127 meters. I found that there's much more change in the y position than there is in the x position. These are the position time graphs found from the experiment. The x position time graph on the left shows rougher oscillations compared to the y position time graph on the right. I'll explain why this might be later on. I put 0.402 for the mass and used the initial position that I found in the tracker for the position in the computational model. I started at time 0 and used 1 over 210 for my delta t. I entered the spring constant that I found earlier and the relaxed length of the spring that I also found earlier, using these equations. The L vector is equal to the ball position because the spring position is equal to the origin. I found the kinetic energy, potential gravitational energy, and spring energy using these formulas. The total energy is equal to the sum of these three other energies. I set the runtime to be 7.787 because that's when the video ends. Gravitational force is equal to negative mg, and spring force is equal to the equation brought up earlier in this lab. F net is the sum of these two forces, because these are the only forces acting on the object. I use the velocity update formula here and the position update formula here. The energy formulas are repeated here, so the model can update their values. The delta energy values are used for plotting the energies. This video shows that the computational model is similar to the actual video in the y component. Since the x initial position is so close to the y-axis, the computational model has trouble modeling it. The motion of the two balls is not in sync because the computational model starts the moment before the ball is released, while the tracker data starts with the man pulling the object down and to the left. The y position time graph shows the model and the observed data are very similar in frequency and wavelength. The x position time graph shows that both the model and observed motion oscillate at about the same frequency, but the amplitude of the observed is much less. This is due to error, and the amplitude should be more similar. As we can see from the graph on the right, all the energies oscillate as the object oscillates. If the spring is compressing, the potential spring energy is increasing. If the object is increasing in height, the gravitational potential energy is increasing. If the object is speeding up, the kinetic energy increases. Since these energies always sum to 0 joules, the change in energy is 0. There were several possible errors in this lab. In the tracker software, it's difficult to perfectly place the center of the object at each time frame, which leads to some inaccuracies. These inaccuracies are amplified by the x position being so close to the y-axis. Also, the man releasing it may have added some force to it, adding some more inconsistency. The air resistance also may have slowed down the object. An incorrect initial x position seems to be the most likely cause of the issue with the gap between the model and observed x position graph. I used the data point from tracker for the initial position, so it's difficult to explain why this discrepancy exists. The energy principle is satisfied by this example. All of the energies in the graph cancel out if they are summed together. When gravitational potential energy is at its highest point, spring energy is at its most negative, canceling out when kinetic energy is also added in, meaning that the change of energy is zero. When I estimated an oscillation period from the x position, I found that it was 1.646, while when I estimated one from the y position, it was 1.519. They're very similar, but the y position is more accurate since it gave a smoother, more reliable oscillating graph. Thank you for watching my presentation.